The last thing we'll talk about here is the regulation of enzyme activity, and there are four main mechanisms to regulate enzyme activity. And when we talk about regulation of enzyme activity, we're basically talking about what can turn enzymes on and off. So we don't want enzymes to be on all the time in our body. That doesn't make sense. That's not efficient, right? We want them to be regulated based upon need. So we only want, for example, lipase to be working if there are fats to be broken down. If there aren't any fats, we need to turn lipase off. So these four mechanisms are how we regulate enzymes, basically how we can turn them on and turn them off depending on needs in the body. So the first one is allosteric regulation. And this is basically a modulator that's present. It's going to bind to the enzyme at an area other than the active site. So it's not binding at the substrate site or the active site. It's binding somewhere else on the enzyme. And basically the presence or absence of this modulator can turn the enzyme on or turn the enzyme off. Now the modulator can be a lot of different things. It can be functional groups that are bound because of certain levels of substrates or levels of products. And so basically, it binds to the enzyme, and depending on what is best at that time, what's most efficient, it'll turn the enzyme off or turn the enzyme on. The second mechanism is covalent regulation, and this has to do with binding of some type of chemical group. This is a very prevalent method of regulation in the body. We're going to see this very often as we go on. And covalent regulation usually happens with a phosphate group as this chemical group, but it can happen with other chemical groups as well. So basically you have the enzyme in question, and then you have another site which binds a functional group, again, usually a phosphate. And then we have two other enzymes present. We have enzyme A, and enzyme A basically adds a covalent group onto the enzyme in question. So it's going to bind phosphate, for example, to the enzyme in question, and the binding of that phosphate is going to turn the enzyme either on or off. Very important to recognize here that this can be turning it on or off depending on the location in the body. So basically, we alter the enzyme's activity in the presence of this functional group. On the other hand, we have another enzyme present which can break that covalent bond, break that phosphate off, and that will make the enzyme do something else. So if having the covalent bond turn the enzyme off, cleaving the covalent bond is going to turn the enzyme on, and vice versa. Again, this can differ greatly depending on exactly where we are in the body. Sometimes we see that phosphorylation turns something on, sometimes we see that phosphorylation turns something off, and vice versa. So looking more closely at this example, protein kinase is one type of enzyme, and we have enzyme X here on the other hand, and this is the enzyme in question, and we can bind a phosphate to enzyme X. With the help of protein kinase, we can turn this into an enzyme phosphate complex. So this phosphate is bound to the enzyme, and it's going to be catalyzed, or it's going to change its catalytic activity, either turning it on or turning it off. And in the opposite way, we can have this enzyme phosphate complex, and we have a phosphatase, which is a different enzyme that cleaves the phosphate off. And again, that can turn the enzyme on or turn the enzyme off. We're going to see a lot of examples like this in the body. We're going to see it in muscle when we talk about creatine kinase. We're going to talk about smooth muscle contraction with myosin light chain kinase. And basically that phosphorylation versus dephosphorylation is a really important method of regulating, where we can turn something on or turn it off. The third mechanism is feedback inhibition. And this is basically regulating the rate of a single part of the reaction or a single enzyme based upon the substrate concentration of another product or substrate. So in this first example of feedback inhibition, the rate of enzyme 1 and the rate of enzyme 3 are pretty much constant, whereas the rate of enzyme 2 in the middle here depends heavily on the concentration of substrate C. So if we have a lot of C, we're going to turn enzyme 2 off, and that makes sense. If we're making a lot of C to kind of slow down the process and pump the brakes, we can turn off enzyme 2, and that'll decrease our concentration of C. If we have a little bit of enzyme C or too little, we can turn enzyme 2 on, and that's going to speed up the process and we're going to generate more enzyme, more substrate C. So that makes this part of the reaction the rate limiting step, because the product or the concentration of C is what determines whether the enzyme will proceed faster or slower, and we call it the rate limiting step. Another example here, we can have regulating an enzyme that is downstream. So the first example regulated an enzyme that was upstream. This example regulated an enzyme that's downstream. So once again, the rates of E2 and E3 are constant, but the rate of this first enzyme depends on the concentration of the final product. So if we have a lot of this final product, we can turn this thing off, enzyme 1 off. But if we have too little of this product D, then we're going to turn this enzyme on. And again, that makes sense, right? If we have not enough of product D, then we need to turn this enzyme on so that we can ramp up production, ramp up the rate of the equation, of the reaction. And then the last example here of feed-forward activation is very, very, very rare. Okay, we don't see it very often in the body, but it's basically a substrate that is downstream influences the rate of an enzyme that is upstream. And this is going to be in the opposite direction. So if we have a lot of the substrate B, we basically are going to turn off the enzyme 3, okay? Or turn on, I'm sorry, the enzyme 3. So if we have a lot of B that's building up, then we need this reaction to kind of go faster. So we're going to go upstream and turn on or increase the rate of enzyme 3. Whereas if we have too little of substrate B, then we are going to turn off or decrease the reaction of enzyme 3 because we don't need it as much, right? We have a little bit of B, and so the reaction can proceed in a